Right now, in the same ocean, at the same time, 3 separate natural systems are all spiking at once. Hawaii's most active volcano just fired off its 54th eruptive episode in under 2 years, a pace it has never sustained before in recorded history. A volcano in Vanuatu just produced what appears to be the largest eruption in its known history, punching an ash column into the stratosphere in the middle of the night. The Pacific Ocean itself is running a fever, with sea surface temperatures pushing toward record highs as a powerful El Niño builds toward its peak. None of these 3 things are secretly causing each other, but all 3 are happening in the same ocean basin, in the same narrow window of time, and together they paint a picture of just how active the Pacific has become. Let's start with Kilauea, because what's happening there right now is genuinely record-setting, and it doesn't need any exaggeration to be remarkable on its own. Kilauea, on Hawaii's Big Island, has been erupting in a distinctive pattern since December 2024, episodic lava fountain events at its summit, each one separated by a period of recharge where magma builds pressure again before the next episode fires. As of late August 2026, Kilauea has produced its 54th episode in this sequence. To put that number in context, the closest historical comparison is the Piu-U eruptive period in the 1980s, when Kilauea produced around 46 distinct eruptive episodes, but that sequence played out over roughly 3 years. The current sequence has already surpassed that total episode count in under 2 years, meaning Kilauea isn't just erupting more than it used to, it's erupting on a noticeably faster cycle. Each episode follows a recognizable rhythm. Lava fountains climb rapidly, sometimes exceeding 100 meters, over 300 feet in height, throwing incandescent rock, volcanic bombs, and molten spatter high into the air above the crater. The most intense fountaining typically happens early in each episode, a strong initial pulse that then settles into a steadier, lower output before the episode winds down entirely, usually within about 10 hours. Scientists monitoring the volcano use ground tilt instruments to track this cycle in real time. As magma drains from the reservoir beneath the summit to feed an eruption, the ground physically tilts downward, measurable to fractions of a degree. As the reservoir recharges afterward, the ground tilts back up. That tilt curve has become one of the most reliable ways to anticipate roughly when the next episode is likely to begin, and it has shown a consistent pattern of recharge periods shortening over the course of this eruptive sequence, part of why the episodes have been arriving closer together over time. There's also a structural story unfolding beneath all of this activity. Kilauea's summit caldera experienced a major collapse back in 2018, a dramatic event where the crater floor dropped in a series of large collapse steps as magma rapidly drained from underneath it, largely because that magma erupted instead through Kilauea's East Rift Zone, devastating the Leilani Estates area and destroying more than 700 homes in one of the most damaging eruptions in the volcano's modern history. In the years since, the current eruptive episodes at the summit have slowly been refilling that collapsed caldera floor with fresh lava, layer by layer, each episode, adding another thin sheet of rock to the crater floor. Whether the caldera continues to fill in steadily or experiences another significant structural change in the future depends heavily on how full the magma system stays and whether future activity stays concentrated at the summit or shifts back out toward the rift zones the way it did so destructively in 2018. Monitoring data has also shown occasional upticks in ground deformation along the East Rift Zone coinciding with this eruptive sequence, including activity following a moderate magnitude 5.2 earthquake at an offshore seamount that's part of the broader Hawaiian volcanic chain. Episodes of rift zone inflation are watched closely by volcanologists precisely because that zone carries the historical memory of 2018, and any renewed signs of magma moving that direction get flagged and tracked immediately, even when, as has generally been the case recently, the activity continues to be concentrated at the summit rather than moving downrift. None of this makes Kilauea an immediate threat to nearby communities in the way the 2018 rift eruption was. Summit eruptions, contained largely within the crater, are a fundamentally different hazard profile than lava actively erupting through residential neighborhoods, but the sheer frequency of these episodes, 54 and counting, at a pace outstripping anything in the volcano's well-documented recent history, makes this one of the most closely watched ongoing eruptions on the planet right now, and a genuinely unusual chapter even by the standards of one of the most active volcanoes on Earth. It's also worth understanding just how visually dramatic each of these episodes actually is, because the scale involved is easy to underestimate from a distance. During the strongest pulses, lava fountains have reached heights well over 100 meters, throwing incandescent rock high enough that individual falling fragments, some of them substantial. Volcanic bombs are clearly visible tumbling back down the slope of the crater in webcam footage. The heat output from an active fountain of that size is intense enough to generate its own localized weather. Observers monitoring the live feeds have documented small, rotating heat vortices, essentially miniature convective whirlwinds, spinning up directly above the most active fountaining and drifting up the crater's inner slope before merging into the broader plume rising above the vent. It's a vivid reminder that an eruption this sustained isn't just a geological event. It's actively reshaping the local atmosphere immediately above it for as long as that fountain keeps running. The recharge cycle between episodes is just as important to the story as the eruptions themselves. Kilauea's summit magma reservoir sits at shallow depth beneath the caldera, and its pressure state can be tracked almost in real time using tilt meters, sensitive instruments that detect the ground itself flexing by fractions of a degree as the reservoir fills and drains. In the days after an episode ends, the ground gradually tilts back upward as the reservoir slowly recharges with fresh magma rising from depth. Once that recharge crosses a critical pressure threshold, the system essentially reaches its breaking point and the next episode begins. Early in this current sequence, that recharge period stretched out longer between eruptions. More recently, some recharge intervals have compressed to under 2 weeks, which is part of why the sequence has been able to reach 54 episodes in under 2 years, rather than stretching out over the roughly 3 years the 1980s Pu'u sequence took to reach a comparable count. Now let's talk about the second major event. Because while Kilauea has been building a slow-motion record over nearly 2 years, this next one arrived almost without warning. On August 24th, 2026, Manaro Vui, the large shield volcano that dominates Ambe Island in Vanuatu, produced a massive eruption, sending an ash plume soaring to roughly 15 kilometers, about 50,000 feet, directly into the stratosphere. Based on available historical records, this appears to be the largest eruption from this volcano ever documented. It struck at night, and satellite instruments detected the towering ash column glowing brightly against the darkness, cold and reflective high in the atmosphere, before dawn eventually illuminated the ongoing ash emissions still pouring from the crater. The eruption was significant enough that authorities monitoring the region initially assessed the potential for a tsunami, underscoring just how seriously this event was taken in its first hours. Manaro Vui is a shield volcano, structurally similar in type to Kilauea, though it sits inside a caldera that holds a crater lake. A detail that matters because water interacting with rising magma tends to make eruptions more explosive than they'd otherwise be, since the water flashes to steam and adds violent additional force to the eruption. This volcano has a well-documented history of serious unrest. Major eruptive activity struck in 2017 and 2018, sending ash plumes to around 10 to 12 kilometers, severe enough that authorities evacuated the volcano's entire population, roughly 11,000 residents, off the island. That event caused acid rain, destroyed crops, and released significant sulfur dioxide emissions into the atmosphere. Similar major eruptive phases occurred around 2005 to 2006, also producing ash plumes in the 10 to 12 kilometer range, and there was further notable activity in 1995, along with historical eruptions recorded as far back as the 1870s and 1880s. Set against that history, the August 24th eruption, reaching a full 15 kilometers, and apparently the largest event this volcano has ever produced, represents a genuine escalation beyond its own already serious track record. There's an important reason a 15-kilometer ash column matters more than it might sound. The troposphere, the lower layer of the atmosphere where ordinary weather occurs, typically extends up to somewhere around 10 to 12 kilometers over the tropics. An eruption column that punches through that boundary and reaches the stratosphere behaves very differently from one that stays lower down. Material injected into the stratosphere can linger for months, sometimes longer, circulating far more widely than ash and gas that stay confined to the lower atmosphere, where rain and weather systems tend to wash it out relatively quickly. That's part of why volcanologists pay close attention to plume height specifically, not just whether an eruption happened, but how high the material actually went. So here we have two very different kinds of significant volcanic activity occurring simultaneously in the Pacific. One is a long, sustained record-breaking sequence at one of the world's best-studied volcanoes. The other is a sudden, historically unprecedented single eruption at a far less monitored island volcano on the opposite side of the ocean. That alone would be a notable coincidence of timing. But it's happening against the backdrop of a third major story, an El Niño event that is shaping up to be one of the strongest on record. El Niño is a recurring climate pattern centered on the tropical Pacific Ocean, defined by a substantial warming of sea surface temperatures across the central and eastern Pacific, compared to the cooler waters typically found there during neutral or La Niña conditions. It's part of a natural back-and-forth cycle, alternating over a period of several years between El Niño's warm phase, La Niña's cool phase, and neutral conditions in between. But not every El Niño is equal in strength. And the current one is shaping up to be a particularly powerful example. Sea surface temperature anomalies, meaning how far above the historical average the water actually is, have been climbing toward levels that could rival or exceed some of the strongest El Nino events in the modern instrumental record, which stretches back to around 1870. Some forecast models suggest this event could push anomalies beyond 3.5 degrees Celsius above normal in the most affected regions, a genuinely extreme reading if it materializes, and one that would place this El Nino among the handful of strongest events ever recorded. Global ocean temperatures overall have also been setting records recently, with reports of the highest global sea surface temperature readings in the historical dataset occurring within just the past few days of this event unfolding. That's a broader signal than El Nino alone, since El Nino specifically refers to a regional Pacific pattern. But a record global ocean temperature reading arriving at the same moment as an intensifying El Nino adds to the sense that multiple indicators are converging in the same direction at once. Historical El Nino events give us a useful yardstick for judging how significant this one might turn out to be. Instrumental sea surface temperature records extend back to around 1870, and within that dataset, a handful of events stand out as the strongest on record, including a powerful El Nino in the mid-1980s and another notably strong event in 2015 to 2016 that drove significant global weather disruption, including widespread coral bleaching and severe drought conditions in parts of Southeast Asia and Southern Africa. Current model projections for this event suggest anomalies that could match or exceed even those historic benchmarks. There's also a well-documented, though less precisely measured, El Nino event from the late 1770s and early 1780s, an era that predates reliable instrumental sea surface temperature records. But that historical climate, reconstructions and proxy data, things like tree rings, coral cores, and ice cores, suggest was comparably intense. Whether this current event ultimately surpasses that 18th century episode is difficult to say with certainty given the data limitations from that far back, but the fact that it's even part of the conversation says something about how unusual this El Nino is shaping up to be. One detail forecasters watch closely is that strong El Nino events don't always resolve neatly within a single season. While many El Nino events peak somewhere around the November to January window and then fade back toward neutral conditions over the following months, some historically strong. Events have instead persisted across multiple years, weakening only partially before building again, producing an extended multi-year stretch of disrupted global weather patterns rather than a single clean peak and decline. Given how early in the season this event is already showing extreme readings, meteorologists tracking it are treating a multi-year possibility as a real, worthwhile scenario to prepare for, rather than assuming a fast, single-season resolution. One of El Nino's most visible fingerprints is exactly what's playing out across the Pacific Basin right now, a surge in tropical cyclone activity. During El Nino years, atmospheric conditions across much of the Pacific tend to become more favorable for tropical cyclone formation and intensification, while conditions in the Atlantic Basin typically become somewhat less favorable by comparison, a well-documented seasonal trade-off tied to how El Nino reshapes wind shear patterns across both ocean basins. Right now, that pattern is showing up clearly. Hawaii recently experienced impacts from a hurricane that formed and lingered nearby. Multiple tropical systems have been active off the coast of Baja California, interacting with and absorbing weaker remnant systems in the process. Farther west, disturbances have been forming around Guam. A tropical depression has swept through this Philippine Sea, and a powerful typhoon recently tracked past the southern islands of Japan before continuing on toward mainland China. That's a remarkable amount of simultaneous tropical activity strung out across virtually the entire width of the Pacific Basin, from the eastern Pacific near Mexico all the way to the western Pacific near the Asian mainland. Forecasters who track El Nino's seasonal patterns generally expect this kind of elevated activity to intensify further as the season progresses. Late August, when a lot of this current activity is unfolding, is still relatively early in the broader window when El Nino-driven Pacific cyclone activity tends to peak, with October and November typically representing the period when this kind of pattern becomes most active. If that historical seasonal timing holds, the current wave of storms may represent the build-up phase of something considerably more intense over the following 2 to 3 months rather than the peak itself. It's also worth being clear about what does and does not connect these three stories scientifically. Kilauea and Manaravaui are both real, significant, independently documented volcanic events, and this El Nino is a real and significant climate event, independently tracked through decades of established oceanographic and atmospheric science. But there isn't credible scientific support for the idea that these ongoing eruptions are meaningfully driving this El Nino, or that volcanic activity in the Pacific is a hidden variable behind the ocean's current warmth. Undersea volcanic systems do release carbon dioxide, and CO2 is indeed a greenhouse gas. But the scale of natural volcanic CO2 emissions, land-based and undersea combined, is dramatically smaller. and the scale of CO2 currently being added to the atmosphere through human fossil fuel combustion, several orders of magnitude smaller by most scientific estimates. The honest picture is that these are three separate phenomena, sharing an ocean and a moment in time, not three symptoms of one hidden cause. What does connect them, in a real and well-understood way, is the broader question of large-scale volcanic eruptions and global climate, a relationship science does understand quite well, just not in the way sometimes assumed. Very large explosive eruptions, particularly ones that inject significant sulfur dioxide high into the stratosphere, can genuinely cool the planet for a period of time afterward. Sulfur dioxide reacts in the stratosphere to form tiny reflective aerosol particles that linger for months to a couple of years, scattering a portion of incoming sunlight back to space before it reaches the surface. This is a well-documented and measurable effect, seen clearly after major eruptions in the 20th century, where global average temperatures dipped measurably for a year or more, following an eruption large enough and explosive enough to loft sufficient sulfur into the stratosphere. Whether either Kilauea's ongoing activity or the Manaro-Vaui eruption will be large enough, in the right way, to produce a measurable global cooling effect is a separate and much more specific question, one that depends heavily on exact sulfur dioxide output and how persistently that material stays lofted in the stratosphere, details that typically take weeks of satellite monitoring to properly assess after any individual eruption. There's a genuinely interesting historical pattern worth mentioning here too, one grounded in real archaeological and paleoclimate research rather than speculation. Researchers studying major societal disruptions in the ancient world, most famously the Late Bronze Age collapse around 1200 BCE, which saw the sudden decline of multiple major Mediterranean and Near Eastern civilizations within a relatively short span of time, have pointed to clusters of environmental stressors occurring together. Earthquake activity, drought, and in some analyses, volcanic climate disruption, compounding on top of existing political and economic pressures. That period is frequently cited in serious historical and archaeological scholarship as an example of how multiple environmental pressures arriving in overlapping windows of time can amplify each other's social and economic consequences, even when the individual physical events themselves aren't directly causing one another. It's a useful historical lens for thinking about compounding natural hazards generally, without needing to claim any specific causal link between, say, one volcano's ash chemistry and a hurricane's wind speed on the other side of an ocean. So where does that leave us practically, watching this unfold in real time? Kilauea remains under continuous, sophisticated monitoring by the Hawaiian Volcano Observatory, using exactly the kind of ground tilt and seismic instrumentation described earlier, and scientists there have a strong track record of anticipating the rough timing of upcoming episodes in this ongoing sequence, even if they can't pin down the exact hour in advance. Manaro-Vui's activity is being tracked through satellite ash and sulfur dioxide monitoring, the same systems that flagged the plume height and triggered the initial tsunami assessment, and authorities in Vanuatu, drawing on hard-won experience from the 2017-2018 evacuation, are positioned to respond quickly if the situation escalates further, and the ongoing El Niño is being tracked through an extensive global network of ocean buoys, satellite sea surface temperature measurements, and atmospheric monitoring that has been refined over decades, specifically to track exactly this kind of event as it develops. What ties all of this together isn't a single hidden mechanism, it's simply the fact that the Pacific Ocean is an extraordinarily active place, geologically and atmospherically. And right now, several of its most consequential systems, a record-pace volcanic eruption sequence in Hawaii, a historic eruption in the South Pacific, and a major climate pattern building toward its peak, all happen to be active at the same time. Scientists studying each of these phenomena aren't treating this as some singular unprecedented crisis triggered by one another. They're treating it as exactly what it is. Multiple significant, independently monitored natural events, each with its own well-understood physical mechanism, occurring within the same ocean basin during the same eventful stretch of 2026. That's genuinely enough to pay attention to on its own without needing to reach for any connections beyond what the data actually shows. Kilauea will very likely keep erupting in this pattern for some time yet, based on how the sequence has behaved so far. Manaro-Vui's activity will be watched closely in the days ahead to see whether the August 24th eruption was a singular event or the opening act of a longer eruptive phase, the way its 2017-2018 activity unfolded. And this El Niño will almost certainly continue driving unusually active cyclone conditions across the Pacific into the autumn months, consistent with how strong El Niño events have historically played out. 3 real stories unfolding together in the same ocean at the same time. That coincidence of timing is itself the story, and it doesn't need any embellishment to be one of the more remarkable stretches of natural activity the Pacific has seen in recent memory. There's a broader lesson in watching these 3 systems unfold side by side, one that has less to do with any single alarming headline and more to do with how science actually tracks a moving, complicated planet. Volcanologists watching Kilauea aren't reacting to the Vanuatu eruption. Meteorologists tracking this El Nino aren't factoring undersea lava flows into their sea. Surface temperature models. Each of these fields has its own instruments, its own decades of baseline data, and its own well-tested methods for separating genuine warning signs from ordinary background activity. What makes this particular stretch of time notable isn't that one hidden force is pulling all the strings behind the scenes. It's that the ordinary background activity of an extraordinarily dynamic ocean happened to spike across 3 different systems within the same few weeks. A reminder that the Pacific, at any given moment, is quietly capable of far more than most of us tend to notice until it all lines up at once.